Hi, my name is Manuela Cabrera, and today I am going to talk about the analysis of extended hollow bolt joints to concrete-filled steel columns, specifically the combined failure intention. So steel hollow sections with concrete infill have become popular in high-rise constructions due to the many structural and architectural advantages. For instance, they offer an enhanced load carrying capacity, ductility, and rotation capacity. In this configuration, column walls limit the concrete fracture as well as they limit buckling. And of course, they offer a higher fire resistance. So we have this powerful configuration, but we don't use them as much in construction as connections can be overcomplicated, as this one, for example, because there is the lack of access to the inner part of the column to install standard bolts. So it is here where the research at the University of Nottingham comes into action, as we want to present a fastener that can be easily installed on site, and it is safe and, more importantly, efficient. Blind fasteners have been developed to overcome these limitations, so they can be installed from one side only. It is the case of the extended hollow bolt, which has a geometry that changes during installation, creating a clamping force between the connected members, and it also creates an anchoring effect with the concrete surrounding the bolt. However, as you can see here, there are many complex interactions in this kind of fastener, and they have not been fully understood yet. Therefore, we are working on understanding these complexities in order to produce a blind fastener that can be widespread the use of steel hollow sections in construction. Now, from the literature, we have identified three possible failure modes of the connection. First of all, we have the bolt fracture, which is usually known as strong column, weak bolt. Secondly, we have the column face fracture, which is opposite to the previous one, where we have a strong bolt and a weak column. And finally, a combined failure mode where all components contribute to deformability. From the literature review, we have seen that this combined failure has not been addressed yet. Understanding this combined failure mode, which is the actual failure at which the connection will be subjected in structures, will allow to widespread the use of concrete-filled sections in construction. So in order to understand this failure mode, the first step taken has been the development of a numerical model that combines two independent validated finite element models that simulate the behavior of these two extreme cases. So if we look at the bolt failure component, we took data available from the literature from a total of 51 monotonic tensile pull-out tests performed in single extended hollow bolt connections. In these experiments, a rigid box was used in order to limit the box failure and only study the bolt fracture. A finite element model was developed, taking advantage of symmetry in terms of geometry and loading conditions, and to simulate this kind of failure mode. From the results, we can see that the model not only predicts the failure mode, but also accurately predicts the strength and stiffness of the connection within a 90% prediction band. Now, similarly, for the case of the column fracture, we have taken information from 35 experimental tests, in this case performing groups of extended hollow bolts. For this type of experiments, the authors use a simplified geometry rigid bolt in order to limit the fracture and base the study only on the column face. We developed a model, again taking advantage of the symmetry. However, we used the exact geometry of the bolt in order to make it compatible with other finite element analysis. From the results, we can see that the model predicts well the component initial stiffness and strength, also the failure mode. However, the secondary stiffness at this point is not well captured. This is mainly attributed by the difference in the bolt geometry. As I explained previously, we use the exact geometry of the bolt, while in the test they use a simplified geometry. But in general, we can see that the general behavior is well predicted by the model, so it is considered validated. So we use the previous two finite element models that were validated to produce a combined failure model, which has the actual stress-strain relationship and elasticity properties of all components. In this case, we also use the symmetry, assigned appropriate boundary conditions, and the load was applied as a displacement control boundary condition at the ball head. We monitor both the ball head displacement as well as the column face displacement. So the load displacement curve has shown to have 4 regions, and these 4 regions are based on the plastic load, which is defined as FP, which is the peak load before the component strengths start falling again. So the first region is between 0 and 20% of FP, where all components behave in their elastic range. And at 20% of FP, we start seeing the first sign of concrete crushing around the anchor knot. Then if we further increase the load up to 64% of the plastic load, we observe strain in the column face reaches a plastic value, and there is a stress concentration in the bolt. Now, in the region between 64% and the plastic load, we saw concentration of stresses in the sleeves as well as in the bolt shank. Now, when we reach the plastic load, we have reached the ultimate tensile capacity of the bolt, where it starts necking, and then after this point, the component strength is only dependent on the properties of the bolt. So this has shown us the development of failure of this component, but we also wanted to evaluate the variation of a ball grade and the effects that this could have in the general behavior of the component. So the results from a parametric study changing the ball grade from 8.8 to 10.9 has shown that both the stiffness and strength of the component are increased. And if we look specifically at the graph of a ball grade 10.9, we observe that there are also 4 regions similar to the previous model. We also observe high concentration of stresses at the beginning of the graph in the concrete, followed by concentration of strain in the column face, and finally, near the plastic load, we start seeing concentration of stresses in the bolt. However, in this case, the bolt didn't neck, but it started slipping and pulling out of the section, meaning that a change in the ball grade changes the mechanism of failure from ball necking to ball pull out. Now, it is clear that changing the ball grade has a significant effect on the component behavior, but this has only been performed in a numerical analysis. So we have proposed a test setup in order to continue studying the component behavior in an experimental way. The test setup includes a Concretefilled steel section. We also have a T-stop, as you can see here, which simulates the beam. We have the extended hollow bolts and multiple supports to perform the test. We also have proposed a range of parameters, including concrete strength, ball diameter, ball grade, slenderness ratio, which is dependent on the column thickness, ball gauge, which is the distance between the bolts, ball pitch, in case we want to study different rows of balls, and finally the embedment depth, which is based on the ball shank length. Now, to conclude, we can see that this study has provided important steps towards the understanding of the behavior of the combined failure of the extended hollow ball connection by presenting a validated finite element model that can predict the variation of ball grade. More detailed conclusions include that the first failure signs for both grades studied in this particular study are caused by concrete crushing accompanied with hollow section yielding. After this, the concentration of stresses happens in the bolt, causing either ball necking or bolt slippage. The use of a higher ball grade, in this case 10.9, increases the component strength and stiffness when other parameters are kept constant, such as ball diameter, ball chunk, concrete strength, and column slenderness ratio. And variating this ball grade has changed the failure mode, again from ball necking to slippage, which means the available analytical models for ball grade 8.8 are not applicable for 10.9, and it is a different failure mode. We have also concluded that further studies are required in order to fully characterize this component failure, and an experimental program has been proposed in order to continue these studies. Now, thank you very much for your attention. I will be happy to take any questions you have at the moment, and here are also my contact details if you want to discuss any specific details of my research.